All right, the moment you've been waiting for. Adrian Cole. He's an engineer at Tetrate. He's been working on open source projects for over 10 years, and these days he spends a lot of time on wazero, the zero dependency WebAssembly runtime for Go developers. His past notable project work includes Zipkin, OpenFane, and Apache JClouds. Please welcome Adrian Cole, WebAssembly for the backend.
Thanks very much. Oh, yeah, I guess I need a clicker, don't I? So I do have some things to say about WebAssembly. If you're interested in that, don't leave. Yeah, so I'm an open source late bloomer. I spent a lot of time as like a systems engineer until about maybe 15 years ago, starting in open source. And I tend to gravitate towards like buzzy projects somehow. It was not my intent. WebAssembly is recently buzzed. It happened after I started on it. And one of the things that I'll bring up through this presentation is some things about this runtime that I work on, because I like to do practical presentations with things that you know and you do every day, and that's what I do every day. So if you want to see also side effects of that, you can check out my GitHub. It's code from the crypt, or you can follow my snarks on Twitter. And if you want to stay here or go, it's up to you. Although I've kept you hostage due to my laptop problems, there's still a chance to run away. WebAssembly is effectively a way to run third-party code in your application or your infrastructure. And this is not going to be about the web browser side of WebAssembly. There's plenty of presentations by people who actually work on web browsers, which I don't. Again, I want this to be about what I can share like uniquely with you. And it's also not going to be like a narrative of one specific use case. The way that I'm working on this is to try to connect to different people who are working in different things. And the approach is to go from an abstraction level like higher to lower. So like service abstraction, application, and then down to programming with use cases along the way. And yeah, that's how this runtime thing comes into play, because these are all people that I work with on every one of the things I'm talking about. But WebAssembly is about running any kind of language that somebody desires to host. So you know, Go is just one of them. There's lots of languages that work as WebAssembly. So okay, so starting with service architecture, I'm going to go into service architecture, like how it actually runs in today's infrastructure, to bring out some conflicts that I think WebAssembly can help with. So we often heard presentations in the past like decade about breaking monoliths, and we have these monolithic code bases or monolithic apps, and we're trying to chip pieces away so that you don't have to like have a huge build process and link everything together. And a typical way people have been doing that is through services like REST services or gRPC, chunking bits off that either aren't necessary to be in a big build, or for scaling reasons, or whatever they are. And so they end up being separate processes, or sometimes tricksters do things with Unix domain sockets. But anyway, it's not in the same process anymore. And WebAssembly is an interesting way to deal with a monolith, because you get some of the benefits of like an RPC based interaction, where you have a completely different code base which has a different life cycle than the thing that it's used by. But instead of it being across a remote link or a quasi-remote link, it's actually embedded in process. It doesn't have to use even I/O or anything, just memory communication. So it's an alternative tool in the box. And there's some interesting attributes to that. Again, I'm talking like high level right now, so architecture. So if you think about that, you're not actually provisioning anything to handle a different kind of load. You can, of course, do that, but there's some interesting aspects to that. something to think about. And if you are already doing remote services with like protocol buffer space services, there's an interesting project and a link in the corner here, which you probably can't read, but I'll post the notes. But it's by the lead developer of Trivy, Tepe, who has a Go plugin, which is a neat thing because it allows you to put your toe in the water before learning too much. And you can basically use protocol buffer services to define plugins that are actually implemented with WebAssembly. So it's kind of a neat trick to get a step ahead if you are just tinkering or want to try out things without knowing too much. Now I'm going to talk about a specific kind of monolith, which is appearing much more often these days, which are sidecars. And sidecars pretty much end up by nature monolithic because they're tasked with tons of different types of requirements from different sites into one code base. And it's you want a single image for people to distribute these things on, which basically you find that sidecars tend to be highly customizable, tons of switches and things for routine configuration, but they're also tricky to change, and they can be coupled with versions of other things. One of the more common version couplings would be like folks who use SDO. Its sidecar envoy tends to have a very tight version relationship between the two, and you can't like use any given version of envoy and any given version of Istio and expect that to work well. Even outside of that, sidecars have different types of constraints to them. So Dapr is another type of sidecar for service communication, and it's more like an integration really. But they have a strict static binary policy, so they don't allow any native libraries or any kind of like stuff that's not in the box. So that affects how they can do plugins and things. Whereas, for example, Envoy will allow native libraries if you set up a filter plugin like that. So I'm going to take a pretty easy path description of sidecars because I know it's not familiar to everybody. But let's say that you have an application and typically you would be like as a Spring developer or something like that, you'd have some filters that do some logic, maybe putting in your company's header that you need to have in all of your HTTP traffic. And one basic thing for sidecars is that they can take that configurable logic and then pull it out of the app for you. So you could just configure something to do it and then have it applied to all the apps instead of having to replicate the same logic in like a million different things. And so that's like one of the cool cases of it. Of course, they usually do more like TLS for you and other things, and also some they help with responsibilities of routing. But let's just say you're just talking about filters. So in the case of Dapr, there's middleware that you can configure, and basically your app yields that responsibility to the sidecar. It communicates with localhost, but the traffic ends up going where it needs to go. And you could come into a conflict in this architecture because before you had all the control over the world, you could put filters in different places with your config, or if you didn't like it, you could just build a different filter into your app. But now you've yielded a responsibility to the sidecar, and it doesn't have exactly what you want. So say, for example, it has a regex filter, but it doesn't allow you to use the match expression in the result, or something weird that doesn't quite work. So if you had all the control in your app, you could just do it. And if the sidecar is doing it and something needs to be in front of something else, then now it gets trickier. So effectively, you want the benefits of the sidecar, but you want a little bit of control. And you don't really want to build the whole sidecar app. So the way it works in practice with WebAssembly is similar to how APIs are contracts for what you do across services. And in WebAssembly, the term is called ABI, which is a general term used in compilers, but it's used also in WebAssembly. And that's the contract between the host that's running third-party code and the third-party code. Defines what functions they can import and export, stuff like that. And so Dapr for HTTP middleware, it supports a specific ABI contract, which will allow it things like access to HTTP method and headers and skip the next handler in the chain or return the response immediately, like functions like that that would be normal HTTP handling. And so anything that can compile to that contract can be used in Dapr without Dapr's permission, without recompiling, without worrying about the version of the infrastructure. It can just load it and execute those software. So in a way, because you're allowing more functionality to be added dynamically to the sidecar, it has a monolith breaking effect. You have less pressure because people have another opportunity to do things like this. And an alternative to WebAssembly, you might have like something with the Lua script or some other scripting support inside of these things. So you can think of it in that way. And basically the way it works is that something would configure the location of the binary that has a custom logic. It has a .wasm extension, and then it would just load it. Usually at startup time. Usually they don't change those things during request processing. It's a configuration step. So I'm putting a summary on each of these sections because I know it can get lost easy. But basically, WASM are binary, like for the WebAssembly virtual machine that it can execute. And you can, in a service architecture, you usually have a distributed stuff, so they can be distributed by config maps if they're small enough, or OCI images if they're larger, or just because you prefer that. And it allows you to inline third-party code instead of baking something into the build or using something like RPC to access third-party logic. And that allows you to avoid some complexities of remote deployment and availability. So that's why WebAssembly tends to be used for extensions in service architecture. You see them in different things. Envoy, what I mentioned earlier, has been using WebAssembly as an alternative to Lua for their stuff, and in something called proxy WASM. Yeah. So let's move down one layer to containers. So I put this section in here because there's been recently a lot of marketing about Docker and WebAssembly and some quotes flying around. I don't re-quote people's quotes, but basically there's buzz, so I figured I'd put it in. And I'll start talking about this thing called WASI, which is often thrown around. And so WASI stands for WebAssembly System Interface. So it's like a POSIX layer for system calls. And most things in WebAssembly start with WebAssembly. So container images, as we would know if we're using Docker, things like it, they're platform specific. There's metadata around the image to prevent you from accidentally trying to run a Darwin binary on a Linux host or whatever, to just basically help inventory the blobs on there. And so if we're doing builds with Docker, usually we're going to have a platform that's either implicit or explicit if you're doing a multi-platform build. And then we even have this cool thing called from scratch, which allows you to reduce it not to operating system free, but at least down to kernel level, so that anything from scratch can work with anything with a compatible Linux kernel. And then you could throw a statically compiled binary and have just one really small layer and no operating system, and it's really neat. But in reality, there's a lot of applications, interpreters, and things like that that need more than what they can statically compile. And so they may need to link against libc or OpenSSL or something like that. And I said complicating deployment, but I'm really talking about the image baking process. And the one funny thing about WebAssembly is it has no operating system. WebAssembly doesn't really have Linux on top of WebAssembly. Although there's a very interesting project I should have linked called Container to WASM, which does basically that. But it wasn't intended to do that. WebAssembly has just a virtual machine, very simple thing. And then on top of that, there's the ability to import and export functions. So WebAssembly's system interface is basically functions like read directory, open file, close file, system calls, get random information, and so it can have like a mini subset of things that programs would use. And if you believe that it has no operating system, then you would believe that compiling anything to WASM would be removing platform dependencies, because if it has no operating system, it can't have something on top of the operating system like libc or something else. So it actually has a neat simplifying effect, which means that you could compile something that usually would never run on Windows to actually run on Windows, because if you can manage to get to a compile it to WASM, it will probably work on anything. And that's pretty cool, because even if anyone here has worked with Windows, I certainly do, you know, like Docker isn't exactly the same. FreeBSD doesn't work like in Docker naturally. There are things that limit our portability, and we can hand wave them all by just saying like, I only pay attention to Linux. But in real life, there's still operating system constraints. Now, don't get too excited. WASM containers are emerging, meaning that this is like, for example, the feature in Docker is literally referred to as like a preview. But let's still talk about the neat things. So in WebAssembly, if a container is, if the runtime allows using WebAssembly, then when you say from scratch, it's not talking about a Linux kernel there. It's actually talking about a WebAssembly VM with WASI available. And so you're going to plop whatever you've compiled to WASM, which I put an interesting example that like Python, you can compile that to WASM. Ruby, PHP, you can compile an interpreter, you can compile a program, it doesn't matter. You can compile code to WebAssembly. And if you're using something like an interpreter, then it would need to have access to standard libraries, and you could put those on the image too. And if you were to look at the image result of it, at the bottom you can see like a smaller image size. That's usually the case, but not always. So always look, don't assume it will always be smaller than an operating system. You see VMware Labs here. VMware Labs has a neat project called WebAssembly Language Runtimes, I think it's called. And that one has like proven builds for Python, Ruby, PHP, stuff like that. So it's handy. If you're looking at what are the goals of a WASM container, it's basically to extend the features that people are accustomed to for normal programs that are put into Docker images to WebAssembly programs that were compiled. So if you're using WASI, it's basically it's allowing a compiler to turn a main function into this format instead of a normal object file. It still ends up having arguments, environment variables. It may need to read files. So all those things that you do with normal programs, you may need for WebAssembly. You may need to say, like the arguments to Python, or a variable that it may need to read. And so Dockerfile is still useful for those type of programs. And I put like, what is the actual net gain for having like Docker or your favorite like Podman or whatever your favorite utility is natively integrate with WebAssembly. It's mainly to take away the idea of running a runtime. So a WebAssembly runtime is sort of like a Docker command, which in the case of like wazero, we have a binary that says wazero run, and we intentionally use Docker arguments. But instead of like manually running this thing, you'd have it implicit. So that's why I put this slide like it is. You don't need the layer to put the runtime in there, and you don't need to be as explicit with the arguments. That's kind of cool. So definitely declutters and makes it easier. But yeah, they are limited. You'll hear this come up a lot of times because the POSIX layer has only like 44 usable system calls. So it can't like do things like outbound sockets. You can't launch processes. You can't do signal handling. You normally use like hundreds of things. So like not all things will compile to WebAssembly with WASI. Yeah, they may not be more efficient. Sometimes people like jump to the gun. They'll say, oh, it has really fast start. But then they assume that there's not other ways to make things start fast. And then oftentimes people who are bragging about WebAssembly forget to measure the actual memory usage, which could be like 1,000,000 times more than normal. So I'm, former observability background, just measure things. Don't assume anything. So the summary here is that if you're talking about WebAssembly applied to containers, it's like a limited operating system, and it's already being integrated to OCI runtimes. It's already in crun, for example, this basically gets you to merge those benefits of containers with the WebAssembly virtual machine, which is like a lightweight VM. All right, next down, application. So this is where I'm going to talk about it being like embeddable as a virtue. So one of the ironies about the integration with Docker and WebAssembly is you're still forking processes at the end of the day, because the way the ecosystem works is that like it forks the process and then has like crun do things, and so it's not really embedded, like in the same process. But if you're making an application architecture decision based on WebAssembly, you should think about this being embedded. So when we look at the use cases for WebAssembly and applications, there's basically two ways to find relevance. One is, are you doing something like forking a process now? Another one is, are you doing like a foreign functions? Like, are you importing a native library, maybe in your same language, or something that can be accessed as a C library? And generally in this space, if you can find this from Christina's Pang, the subprocess to FFI blog, there's a link in my slide deck. It's really cool about the pros and cons of things like that. But basically, if we have functionality that's not built into our language toolkit, or it's too much to rewrite. And this is going to get into like a little bit of technical stuff about how WebAssembly works. So, like I said before, WASI is a way to compile something that would normally be compiled to like a binary that you would otherwise install. Like if I'm using OS X, I'd brew install something and I get a binary and I can run it. So the process of making that binary would be like CC or whatever the language it was written in the compiler. So DC-raw is an image rendering library, so you could like take and resize an image for you. And if you wanted to use that image re-rendering inside of your application, you could either access it as a library or just like fork a process. The way that you would do it if you're using WebAssembly is that you get a handle of the WASM, the resulting binary, or you may have to port it if nobody has made one for you yet. And then you'd need to invoke it. So at the top here, I'm saying like, this is Go programming language. So it's like, run the DC-raw thing with these arguments. And that would be very similar to any given language's like fork exec model. The thing that's different is that in WebAssembly, it's a virtual machine. So one of the cool things is that you can fake out the file system. So when it starts up, which WASI, what it does is when you compile something with a main function to WASI, it renames it to start, basically. And then it exports that, and you can call start. The runtimes would do that. This is like inside the box, so don't worry, you don't have to do this yourself. The other thing that the WebAssembly does is it has its own memory, which is decoupled from the process memory, which is how it doesn't crash. So for example, there's never a real pointer given to WebAssembly. If it thinks that it's having a pointer, it's not. Like you're giving it a mythology. So when the WebAssembly module is instantiated, there's memory allocated to it, which is defined there. So it'd be like 64K pages, like your DOS. And then the start happens, and then it's going to do normal things that a program would do during initialization, read some arguments, maybe read from standard input or whatever file it's looking for, and then write some stuff. But the runtime, regardless of whether you're talking about wazero or wasmtime or any of the other ones, they have ways to intercept system calls. And in wazero, we have the ability to virtualize the file system. So in this case, instead of this reading the input file from a real file, it's actually just reading it from memory. And instead of writing it to standard output, it's also writing it to memory. So the DC raw program thinks that it's doing I/O. It's doing none. There's no actual I/O happening at all. So super fast. And also can't crash. So for example, the developer Nuno, who was working with it before, said like one of the nice things about using WebAssembly is you can gracefully handle crashes and buggy code. So for example, this like DC raw.c has been like copy pasted around for centuries. It has bugs in it. It can't take your app down. Worst you can do is like give it an error. So that's kind of cool. And Nuno's an awesome developer. He's actually been promoted to a maintainer of wazero too. Also works on SQLite. So some folks will be familiar with that project. I asked him, why would you consider WebAssembly instead of the other ways to use SQLite and Go? Of course, the first thing is, should you rewrite it, especially in Go? And of course, it's like, well, this is 150,000 lines of high-quality code. Do you really want to do that? Nope. It's really well written. So the OS layer is quite easily contained in SQLite. It's good software. To interface that with native libraries has problems, not including putting the native library onto disk, which is easier in some cases than others. But also there's some security problems with accessing native libraries. And of course you need the incentive, somebody to ask you to actually do it. The way that he's worked on this, and this is Go SQLite. So this is just a library you can import and would allow you to access SQLite, which is a file-based database. He's made it actually to resemble how foreign functions would usually work. Usually you start a function call, allocate some memory, free it at the end, make some scary call that can crash you, and then return whatever happens. And the cool thing is that it can't crash you because nothing is a real memory pointer. And then there's some interesting differences between this and normal C library calls, notably that it's dynamic. In this case, even what you're calling can be dynamic. So you don't need to do any preprocessors or anything. You can replace the WASM whenever you like. And to that point, if you're writing an application, or if you're considering application architecture, there's basically two ways to deal with the WASM binary itself. So in the case of this library, for convenience, this actually puts the WASM binary inside of the Go binary itself. So when it's compiling, it just embeds it into the same thing. You don't have to distribute files. It's just caked into it. But if you're doing something like a plugin system inside your app, then you can choose to just use any mechanism, files or OCI repository or HTTP refs, however you want. It's just a blob with a .wasm extension. It even has a media type. So you can move it around however you like. You can choose to not move it around. So some of you may know about the Trivy vulnerability and misconfiguration scanner. So they have a lot of stuff baked into the Trivy binary, but also they support custom logic for defining your own vulnerabilities or reprioritizing alerts in WebAssembly. And because it's made as a plugin system, naturally they're going to expose that, at least the ability to choose where the files are and install them and uninstall them. So to sum up for, again, the application architecture, anything compiled to WASI not only can be used as Docker like a normal container, but it can actually be embedded into your normal program. And that has some pretty cool side effects because it can have the effects of forking processes without the damage or the overhead of doing that. And it can also be an alternative to calling foreign functions through C libraries. It's because this is an application architecture decision, the apps decide effectively how they want to handle things. If they want to make their code pluggable, or just convenience of themselves, use other people's code. That's completely up to you. Okay, last section, programming. So, yep, it works, and it's also a work in progress. And I'm trying to be cute here, but when you're compiling something to WebAssembly, you're at least changing the flags to the normal compiler, and sometimes you may be using a different compiler. One of the neat programming languages that's kind of up and coming is Zig. It's kind of like a lower level language. It's pretty well suited to WebAssembly because it has good memory controls and things like that. But one of the neat tricks inside of Zig is that it actually bundles in a C compiler. So you can do like Zig CC and compile C with the same binary. So it's actually a 2-in-1 compiler. And why that's neat for WebAssembly is that it already has to bake in WebAssembly support to support normal Zig going to WebAssembly. So it already has the libraries needed to do that for C code. So instead of like the normal process of like lots of steps to get everything working, you basically extract a tar, you have Zig, you can compile Zig, you can compile C. In my project, we have to do a lot of integration tests with C, and we just use Zig to compile it because it's super easy. If you're working with Go programming language, the first compiler to support WebAssembly with WASI, which is a thing I've been mentioning a million times, was actually TinyGo. And TinyGo is an alternate compiler which has a mission to be going into small places. So not only does it produce small binaries, but it supports like a million different architectures for like anything like little IoT devices, anything. And so TinyGo has a option to compile Go source to WASI, and then the next version of Go 121 will actually support WASI out of the box, which is really impressive to me because a year ago I never would have guessed it would have happened. But the community has really gotten together and made things work, and it's just been exciting. So on one hand, you have Zig that can compile multiple different languages to WASM, and then you have Go, which you have multiple compilers to compile. Maybe not as many options as C, but anyway, you have options. Now let's say another programming step. We hear some marketing says like, well, it's near native performance, or somebody saying like, oh, it's atrocious. Well, how do you deal with those things in normal life? You'd use a profiler. This is something I'm putting here because it's actually quite cool if you think about it. If you do have a polyglot ecosystem, then you can compile different source files to achieve the same goal. They would still be in this intermediate format of WebAssembly. So if you can manage to get your normal tool chains to work with WebAssembly, now you've extended those tools to any language that can compile to WebAssembly. So this is an example of the same like math.c that you see here. We're just not really doing much math. Just printf, and then Go doing the same thing. And what's the output look like? So you would see that obviously C should be less. Doesn't have garbage collector and things like that going on. The other should be more. So one of the things that's interesting about when you're working with WebAssembly as like a sub-process model, you have to go through the process's init phase every single time you invoke the function, which has some cost to it. And how impactful that cost is really your use case. For example, in the wazero project, we usually, a lot of our stuff only initializes in a microsecond or something. So it depends on what's happening, but it may not be of any impact, so you don't even care. But for some people, they care. And so if you're trying to troubleshoot why is it slow, then recently you can use wcprof, which is a tool that can account for memory and all the functions being called and give you heat maps and cool stuff. So I think that's pretty neat. That's why I put that in today. So from the last section, if you get to the programming level, you're actually making something that wasn't working before work with WebAssembly, or you're developing something from scratch, at least you're going to use a different compiler flag. Maybe you can use the same compiler. And I would say don't make any assumptions from blogs about performance and things, because you do have tools and you can use them. But in all, if you're getting to the point of like programming like at WebAssembly's level, expect more work than you'd usually have, and expect more surprises. And it may have some like technical weirdness that you're not accustomed to. And that brings me to, oh, actually, I have a new section I also added today. So some cool stuff, like hot off the press. Kubernetes, a couple years ago, I think, had attempted to use WebAssembly. It was too new. Things weren't working out so well. Now, like as of this week, there's a new special interest group to start scheduler plugins so that you can actually extend Kubernetes scheduler with custom logic. The Dapr project that I mentioned earlier is now doing event handling, like a function as a service use case with WebAssembly. That's super neat because like if a sidecar doesn't even need to launch a process for certain types of events, it's an uncomplicated way to handle some logic. And then for those of you using protocol buffers, buff is at least a alternative to Proto-C, and it has an alpha product out there for custom plugins to its binary. Pretty cool stuff, big projects. So that's all. So got some summary points here. I went through a lot of stuff intentionally because I know everybody has different backgrounds and you won't find everything relevant, but at least hopefully you found something relevant. And lots of links, so just watch for the slide deck if that's interesting to you. And I've got some links for some other presentations that dig into some of the nitty-gritty. I think I've got 1 minute for questions, so over to you, and thanks for your time and patience with the weird laptop stuff earlier.
Thank you, Adrian, for your talk. We have a little gift for you from CraftConf. It's a Budapest notebook, and then we've created this beautiful picture of you, for you.
Wow, it's beautiful and has me in it.
For your ego wall. So thank you very much for being here today.
Thanks very much. Yeah.
And ladies and gentlemen, we don't have time for questions, but if you are around, can people just come and say hi and ask you a question?
Mm-hmm. Yeah, that's why I'm here.
Wonderful. One more time for Adrian Cole, everybody. Thank you.
Thank you.